All right, welcome back to the channel. Today's all about derivatives. I selected 25 really good ones. This is assuming that you've been through most of your rules and you just need a good sort of overview of everything. So let's jump in. The first one uses the product law. We're multiplying, so the derivative, I'll use y prime as well as dy dx interchangeably. You'll see that. First times the derivative of the second plus the second times the derivative of the first. So first is x to the 5 times the derivative of the second. The derivative of tan is secant squared. So secant squared x plus the second times the derivative of the first. So the derivative of the first is going to be, you take the 5 down front and you subtract 1 from the exponent. So 5x to the 4 tan x. Right on. Look for opportunities to simplify, but I think this is probably good for our purposes today. Second one here, this is going to be a quotient, so it's something divided by something. So I'll use dy dx here, just so you get used to the notation. So bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So the bottom times the derivative of the top. The derivative of the top is -1, so negative 3x plus 1 minus the top times the derivative of the bottom. The derivative of the bottom is 3 times 2 minus x, and that can be all written over 3x plus 1 all squared. So 3x plus 1 all to the power of 2. Clean up your numerator, don't leave it like that. So that's going to give you negative 3x minus 1 minus 6 plus 3x all divided by 3x plus 1 squared. Notice that the 3x's cancel, leaving a -7. So that's going to be -7 over, in brackets, 3x plus 1 all squared. Third one here, they're sort of creeping in on each other. Just so you know, if you have a radical, you can always change it to a rational exponent. So that's going to be equivalent to 3 minus 2x all to the half. And then you can treat that just like a normal power rule. So if I take the derivative y prime, I take the exponent, I move it down front, which is going to be 1 over 2. And this has a base 3 minus 2x. We've got to come back to that in a second. Minus 1 from the exponent, which is going to be -1/2. We're not done. Do you know what we have to do? This is called the chain rule. So right here, chainrule, chain rule. Okay, so you have to know where the inside function is. So you take the derivative of the outside function, and then you have to also multiply it by the derivative of the inside function. So 3 minus 2x is the inside function. And the derivative of 3 is 0. The derivative of -2x is -2. So I have to multiply that by -2 to finish that off. So y prime. Notice the 2's will cancel. The -1/2 is upstairs. You move it downstairs, becomes a radical in the denominator. So -1 over, I'll turn it back to a radical, 3 minus 2x. Okay, our next two here. Notice here, it looks like we have to use the quotient rule, but we don't have to. What we could do is take the power downstairs and rewrite it like this. 2 times 5x plus 1 all to the -3 using my exponent rules. And then take the derivative, y prime is going to be equal to, the 2 here doesn't really have to do much, it's out of play, so just keep that in front, it's a constant, and do all the differentiation on the power. Power rule says take the -3, move it downstairs. That's going to be -3 bracket. Just rewrite your base, 5x plus 1. Don't forget to subtract 1 from the exponent. So -3 minus 1 is -4. And be careful, there is your chain rule. That's the inside function, so I have to also multiply by the derivative of the inside function, which is 5. Close your bracket, clean it up. So 2 times -3 is -6 times 5 is -30. And I'm going to just take this downstairs. I don't like to leave it as negative exponents. So 5x plus 1 all to the power of 4. And then this one here, we can take it term by term. So dy dx is equivalent to, I'm just going to use the the exponent rule here, the power rule, bring it downstairs. So bring it down front. So 3 times 2 over 3 is 2x. Subtract 1 from 2 over 3, which is going to be negative 1 over 3. And same here, bring the half down. That's half of 4, which is 2. So minus 2. X, subtract 1 from a half, it gives you negative a half. And the derivative of negative 2 is 0, so I don't have to write anything. And then here what I might do is, just since I have negative exponents, I'll move that downstairs. That's going to be the cube root of x. And then minus 2, that's the square root of x. All right, these next two have radicals in them, so if it scares you, pay close attention. What I would probably do is take all my radicals and write them as rational exponents. So that's equivalent to saying y equals 2x to the half. And then this is a half downstairs becomes negative half upstairs. So there's negative 1 over 2x to the negative 1/2. And then the derivative is just y prime, term by term. Take the half down front. Half of 2 is 1. So I don't have to write it. X, subtract 1, which is going to give me negative a half. And here I'm going to take the negative a half, multiply it by negative a half, which is a quarter, plus a quarter, and then subtract 1. So that's going to be negative a half minus 2 over 2, which is negative 3 over 2. So x to the negative 3 over 2. And in this case, I'm just going to leave the exponents like that. I trust that you'd be able to convert those to radicals. All right, let's look at our next one here. So we have another radical. Don't be afraid to convert that to a power. A radical is just an exponent. If it's degree 2, you can take the whole base, which is x squared plus 2x minus 1, and just raise it to the power of 1 over 2. And then you can use the power law, which is pretty easy for most students. So dy by dx is just an alternative to saying y prime, which is equivalent to, the rule is to take the exponent out front. You got to memorize some of this stuff. Just rewrite the base. So x squared plus 2x minus 1. And the rule is to subtract 1 from the exponent. Why? Because it works. So minus a half. And then don't forget, look, you got a chain rule. So when you have a power, the base itself is the inside function. Take the derivative of the inside function and multiply it. The derivative of x squared is 2x. The derivative of 2x is plus 2. And the derivative of negative 1 is 0. I leave it like that. Let me clean it up a little bit. Look at the 2 down here with the 2 and the 2. This is all in the numerator. I'll put that over 1. So the 2 here will nicely divide into this binomial, leaving 1s. Okay, that's nice. And also, too, I'm going to take this thing, which has a negative exponent, move it downstairs. So that's going to be equivalent to upstairs, the x plus 1. All divided by, well, the radical of this, the square root of x squared plus 2x minus 1. Next one has ln in it. It also has e to the x. So I'll say y prime here for the derivative of y. The derivative, the big function is ln. So the derivative of ln is 1 over what is being ln'd. So 1 over this, I'll write it out, multiplied by the derivative of the inside. Do you see? So we just take the inside, the ln, and we flip it, and then we take the derivative of it. So that's got to be multiplied by the derivative of the inside. I'll use the quotient rule. So bottom times the derivative of the top. The derivative of e to the x is e to the x. So e to the x minus 1 minus the top times the derivative of the bottom. The derivative of the bottom is e to the x. So e to the x times e to the x all over the denominator squared, e to the x minus 1 squared. Okay, let's clean that up. So that's going to be equal to, well, 1 over e to the x over e to the x minus 1 is e to the x minus 1 over e to the x. And then here I can do some expanding through. Don't leave things like that. So e to the x times e to the x is e to the 2x. And e to the x times negative 1 is minus e to the x. Minus e to the 2x here as well, all over all that squared. And notice these are going to cancel. That's kind of nice. You're also going to notice that e to the x is going to cancel with e to the x. That's going to leave a 1 and a 1. And so here what I have, I still have a minus here. So I've got a minus 1. So minus bracket e to the x minus 1 all over this thing in the denominator, e to the x minus 1 all squared. And of course I can cancel one of those e to the x minus 1's, leaving negative 1 over e to the x minus 1. Number 9, this one looks really cool. It's got all kinds of e to the x's. Do you know what the derivative of e to the x is? I know you do. It's e to the x. So let's use that. Just be aware too that when you have a power like this and it's exponential, the inside function is the exponent. So let's use that. So I'm going to start differentiating. This is a quotient, so I'm going to use the quotient rule. Bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So I'm going to take the derivative of the top. The derivative of e to the x is e to the x. And the derivative of e to the negative x is also e to the negative x. But I have to then go inside here. That's not just x, that's negative 1x. What's the derivative of negative 1x? Well, it's negative 1. And that's going to come down front. A negative and a negative is a plus. Do you see? Wrap brackets around it. So that was the bottom times the derivative of the top. So e to the x plus e to the negative x. I know it looks ugly. Minus. So it was the bottom times the derivative of the top minus the top times the derivative of the bottom. Let's take the derivative of the bottom. So e to the x, the derivative of that is e to the x. The derivative of e to the negative x is negative e to the x. So minus e to the negative x. Okay, so that was the derivative of that times the top. So e to the x minus e to the negative x. This is all going to be divided by the denominator squared. This is the rule. This is called your quotient rule in calculus. Don't forget to square it. It's easy to forget. All right, don't leave it like this. I know you want to, but you can't. So let's FOIL or expand or use the distributive property in these cases. This actually is going to be easier than you might think. E to the x times e to the x is just e to the 2x, right? Because you're just adding the exponents. When you multiply two powers with the same basis, you just add the exponents. E to the x times e to the negative x, well, guess what? That's just 1. Because if you add x with negative x, you get 0. E to the 0 is 1. And then e to the negative x times e to the x, well, that's 1 as well, plus 1. This is kind of nice. And then e to the negative x times e to the negative x is going to be positive e to the negative 2x. Okay. Usually these are set up, you know, to sort of simplify not too badly. Okay, so here we go again. E to the x times e to the x is e to the 2x. E to the x times e to the negative x is going to be negative 1. And then negative e to the negative x times e to the x is going to be negative 1 as well, just because these are opposites. These exponents are opposites. And then negative and a negative is a positive. E to the negative x times e to the negative x is going to be e to the negative 2x. Okay. I already can see, just looking at that, I can see some cancellation opportunities all over the bottom squared. You have to write it. This allows you to sort of catch your breath. Okay, next line. E to the 2x plus, or rather, look here, e to the 2x here, and it's being subtracted. So we can cancel those away. Love that. And then e to the negative 2x minus e to the negative 2x. Goodbye. And I'm left with a 1 plus 1 is 2. And in here I've got a negative 2, which is a negative 1 and a negative 1, which is negative 2. And a negative 2 is a positive 2. So 2 plus 2 is 4. Oh my gosh, this really has distilled down into something pretty straightforward. Plus e to the negative x all to the power of 2. There's your final answer. Okay, onward and upward. How are we doing? So this one here has a ln in it, also has secant and tan. It looks scary, but it's not too bad. So let's take the derivative using y prime this time. And the derivative pattern here when you have a log is going to be 1 over whatever is being logged. So that's going to be 1 over secant x plus tan x multiplied by the derivative of the inside function. So for log functions, ln is a log base e. This is the inside function here. So I'm going to take the derivative of the inside. So the derivative of secant is secant x times tan x. And the derivative of tan is secant squared. Sorry, I'm downtown and it's really loud. Okay, so I apologize for that. Okay, and so I noticed something here. I can also take out a secant x in the numerator. So I'm going to take a secant out, and big city living, you know. So tan x plus secant x all over secant x plus the tan of x. Look what I notice. Look, tan x plus secant x is the same as secant x plus tan x. Goodbye. And what's left? Just little old secant. So that's kind of nice. It looked ugly, but it turned out to be pretty nice. So another opportunity to use the ln function. This time I'll say y prime. Don't forget the derivative of ln is 1 over what is being ln'd multiplied by the inside function. And this is the inside function for the chain rule. So I'm going to have 1 over x. And you know what I'm going to do? I'm going to turn that to a rational exponent. You'll see why. And now I got to multiply by the derivative of the inside function. So there's the inside function. It's a product. So this times the derivative of this. So don't forget that this is the same as, I'm just going to write it here, x squared plus 1 to the half, as I'd written here already. So this times the derivative of this. Well, what's the derivative of that? Well, there's your power rule. So bring the half down front. I'm going to put the x there because that's going to be a part of the answer. So this times the derivative of this. Bring it down. And then just rewrite the base. Then subtract 1. That's going to leave negative a half. And uh-oh, there's another chain rule. I've got to take the derivative of the inside, which is 2x. The derivative of x squared is 2x. So I got to times that by 2x. Plus this times the derivative of that. So I'm just going to write that as x squared plus 1 all to the half. The derivative of x is just 1. So close and then clean. Close and clean. So see the 2's cancel nicely. And also, if you look here, I have, I've got this to the half, negative a half. I got this to the half. And I've also got this to the half downstairs. So what I'm going to do is I'm just going to clean it up a little bit so you can see what I'm talking about. So here I've got an x times an x, which is going to give me an x squared. And then I'm just going to leave that as x squared plus 1 to the negative a half plus, in bracket, x squared plus 1 to the 1 over 2. And that's all divided by x squared plus 1 all to the half. Now generally you have to get good with your math skills, okay? So what I'm going to say to you is we can probably simplify a little bit here on these radicals, these rational exponents, by multiplying through. So I'm going to multiply the top and the bottom by x squared plus 1 to the half, both in the numerator and the denominator. Because that's just multiplying by 1, and that doesn't change anything. But watch what happens when I do that. It's going to make it a whole lot easier. I'm going to distribute this through to the 2 terms in the top. So this times this is just 1. That just leaves x squared. How nice. Look, x squared plus 1 to the negative a half times x squared plus 1 to the half. The bases are the same. You add the exponents. The exponent is 0. Anything to the 0 power is 1 except for 0. And then I've also got to multiply it here too. Well, a half plus a half is 1. So that's going to give me plus x squared plus 1 in the top all over. I'm going to do that here as well. That the x is there out front. And then I'll multiply this by this, which is also going to leave me x squared plus 1. All right, I'll clean it up a little bit here. So x squared plus x squared is 2x squared plus 1 all over x times x squared plus 1. Okay, this next one involves arctan. Sometimes it looks like this, tan to the negative 1, or inverse tan. So it could be written also as arctan of x over 2. And what we do know is that the derivative, if I take the derivative of arctan, I'm going to say u, arctan of u, okay, where u is given as a function of x. This allows for the chain rule. That's going to be equal to 1 over 1 plus u squared multiplied by du dx, okay? In cases where you're dealing with something that has an inside function. So for the chain rule for arctan, that's the inside function. Whatever is being arctan is the inside function. Okay, so I'm going to say y prime. I'm going to take this derivative down here. And I'm going to simply use this formula. It's a formula that's usually in the formula book. So that's going to be equal to 1 over 1 plus, in this case the u, my u value is x over 2, which I might as well just take the derivative of now. So du dx is equal to a half, because I'm going to need that for the formula. So my u is x over 2, and that needs to be squared. That comes directly from the formula, the derivative formula. Multiplied by du dx, which is going to be 1 over 2. So the 2 can be brought through in the denominator, so that's going to give me a 1 in the numerator and a 2 plus, now here I've got 2 squared in the denominator of the fraction, but when the 2 comes through, that's going to be actually 1/2. So it's going to give me a half x squared. And because I don't really like having fractions inside my fractions, I'm going to multiply by 2, both in the top and the bottom. So it's going to be a 2 in the numerator and a 4 plus x squared down below, and that's the derivative of arctan of x over 2. All right, we got another one that involves the chain rule with the trig and product rule. So y prime here is going to be the first times the derivative of the second. So x squared times the derivative of sine is cosine at the input, 1 over x. But then this here is the inside function, so I have to take the derivative of 1 over x. Well, what's the derivative of 1 over x? Well, you could use the chain rule, so the bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom, which is 1, all over the bottom squared. So it's actually equal to negative 1 over x squared. So look at that. It's going to make negative, and I'm going to put the x squared right there, which is going to cancel with that x squared. I'm not done yet, plus this times the derivative of that. So the derivative of that, which is x squared, is 2x. 2x times the sine of 1 by x. Let's clean this up. So y prime here is going to be equal to the cosine with a minus in front of it, I almost overlooked that, of 1 by x plus 2x sine 1 over x. I'll put brackets around that as well. There she be. Up next we have 1 over 2 sine double angle, so dy dx in this case is equal to, different ways to handle it. I'm just going to use the quotient law, especially when the numerator is 1, because it's going to create a 0. So bottom times the derivative of the top, 0, minus the top times the derivative of the bottom. So I've got to take the derivative of the bottom, which is going to be 2. The derivative of sine is cosine. I just rewrite 2x. Do you see? You just keep that. But then the 2x is the inside function. So I have to take the derivative of 2x, multiply that by 2, all over the bottom squared, which is going to be 2 sine 2x all squared. Okay, well this is interesting because look, I've got a 2 and I've got a 2 and I've got a 2 and a 2. So the 2's are going to cancel, leaving nothing more than a negative in the numerator with a cosine 2x all over sine squared 2x. Now you could write this in different ways. Often they like to combine the sines and the coses. Do you see you've got a cos over a sine, so long as the angles are the same. So I've got a cos double over a sine double, but that leaves me with one double sine on its own, which is totally fine. So here, cos over sine, you know that's cotan. So negative cotan, double angle, and the reciprocal of 1 over sine is cosecant. So cosecant double angle, there you go. I'll put a box around that, worked for that one. All right, this next one uses the product law, although you could use the quotient law as well. It's got a cosine in it, it's got a double angle, some chain rules, so let's try it. So y prime, in this case, is going to be first times the derivative of the second, plus the second times the derivative of the first. So I'm going to look at the derivative of this, which is negative sine, so I'm going to pull out a negative. I'm also going to have to come inside here. There's my inside function for my trig functions, and I need the derivative of 2x, which is 2. So I'm going to put a 2 here. The e to the negative x isn't being differentiated here. And again, the derivative of cos was sine. So sine 2x plus the second times the derivative of the first. Well, the derivative of e to the negative x is e to the negative x, but there's the inside function. Lots of chain rule going on. So the derivative of negative 1x is negative 1. So that's going to change this to a minus. It comes down front. And just multiplied by cosine 2x. Okay, and then also notice that I can take out an e to the negative x. I'll even take a negative e to the negative x. I don't know, it's good to get into the habit of factoring because usually you have to do that for most of the reasons why you take derivatives in the first place. So 2 sine 2x plus cosine 2x, and I think I'll just leave it right there. All right, the next one also uses the chain rule. It has secant in it, so I'm going to use y prime here for the derivative of y. The derivative of secant, now this is secant squared. You know what I'm going to do before I do any differentiation? I'm just going to rewrite it like this. I'm going to write x to the half all squared. Okay, so this outside squaring means it's secant times secant. I'm not going to be combining those two exponents, okay? This is in the input set. This is squared after the input set has been secanted. Okay, so be careful with that. So now I'm going to get into my derivative. So now look, largely the big function is the power. So I'm going to take the 2 down front, 2 bracket secant, just rewrite the input, subtract 1 from the exponent. You don't have to write 1, but I will. And then here's your inside function. Oh my gosh, we got a lot going on here. We got a double chain. So look, the derivative of secant is secant tan. So the secant of x to the half times the tan of x to the half. But we're not done. I don't think so. Look, we still have this inside function. So we're really going down in the rabbit hole. So I've got to take the derivative of x to the half. Well, that's going to be 1/2 x. I got to subtract 1 from a half, which leaves me negative a half. Let's clean it up. Okay, so look at the 2's are going to cancel. That's kind of nice. And you see here now I've got what, a secant? I think what I'm going to do is I'm just going to put back the square roots. The square root of x times the secant of the square root of x times the tan of the square root of x. And I also have this x to the negative a half, which could be written downstairs as the square root of x. And I can combine that. I've got a secant squared. So I'm going to say a secant squared root x times the tan of root x, all divided by root x. And there she be. All right, let's take this one on. It's the quotient rule. So y prime is equal to bottom times the derivative of the top. The derivative of the top is 2x times the bottom. I'm literally just following the formula. Minus the top times the derivative of the bottom. The derivative of the bottom is negative 2x. So a positive 2x times the top all over the denominator squared. Just say that a bunch of times and you'll remember it. And then clean up the numerator. So you get what? A 2x. I've got to bring the 2x through. Minus 2x cubed. Plus 2x plus 2x cubed. All over the denominator, which is 1 minus x squared all to the power of 2. Check out if there's any opportunity for cancellation. There sure is. Those are going to cancel. That's nice. You take it. And then a 2x plus a 2x is a 4x all over 1 minus x squared, a squared. Okay, number 18 is a little different. It's still after the derivative. In this case, the derivative of root x. The only difference is it doesn't want you to use your rules. We have to use the definition of the derivative. Do you know what it is? Well, there are actually two. I'm going to use the more commonly used one. So I'm going to say y prime, the derivative of y, can be given as, it's actually the limit. It's the limit of the function under study at x plus h minus f at x all over h as h approaches 0. So what this requires is that we figure out what f at x plus h is. So f at x plus h is going to be equal to, well, there's the function. So all I'm going to do is I'm going to plug in x plus h where there was an x. And that also means f at x is equal to root x. Okay? So f of x is equal to root x. This is my f of x function. And f of x plus h is root x plus h. So plug it into the formula. So that's going to be the lim. You have to write the lim each time. Don't drop this. Keep writing it. You'll get your math teachers upset if you don't. So the square root of x plus h minus root x over h. Okay, so with radicals, you know, I'm sure you've heard the conjugate before. So the conjugate here, you can see the conjugate of the numerator is the numerator with a plus in the middle. I'm going to use that because the problem is I can't use a direct substitution here for the limit. If you know your limits in your limit rules, I have a 0 in the denominator, so I'm not going to do that. So what I'm going to do is I'm going to change it up a little bit by multiplying the numerator and the denominator by the conjugate here. So I'm going to write x plus h plus root x all over x plus h plus root x. Okay? And that's just multiplying by 1. So the next stage is to expand the numerator. So this times this, I'm going to expand it out using FOIL, first outside, inside, last. So root x plus h times root x plus h is x plus h. And you can see how useful this is because it gets rid of a lot of the radicals. So x plus h. I know the o and the I are going to cancel. You can expand it out. You'll see it'll work. But then what we have to do is subtract root x times root x, which is just x. All over h times this. So the square root of x plus h plus root x. As h approaches 0, and you can see we get some cancellation. Look at the x's are going to go away. And I'm just going to use the magic of eraser. So don't do this on your test, though. You should show everything. Show all your steps. And then notice the h's will cancel, leaving a 1 in the numerator, which is kind of nice because now look, you can check to see if you can do its direct substitution with your limit. So if I put a 0 in for h here, I'm not going to get a 0 in the denominator. So I can plug 0 in for h at this stage. So the numerator is 1. This is where I drop the lim. As soon as I plug 0 in for h, I don't write lim any longer. And that's going to be the square root of x plus 0, h is 0, plus root x. And well, that's just equal to 1 over 2 root x. Now we can verify that using our rules, because if I was to take the derivative of root x using the rules, well, I could think of that as the derivative, that's actually an equal sign, of x to the half. And I can use the power rule by bringing the half down front, subtracting 1 from the exponent, that's going to give me negative a half. And of course, I can move that downstairs to 2x to the half or root x. And you can see it confirms the answer. There you go. Okay, the next 3 are going to be implicit differentiation. You can see that y is sort of embedded in the equation. It's implicit, it's not explicit or isolated. So we're going to just move right through that using differentiation, because ultimately what I want to isolate is dy dx. I want to know what that is. Okay, so let's get started. Don't forget, we're differentiating with respect to x. So x is the independent variable, which means that if I take the derivative of x squared, if I take the derivative d by dx of x squared, that's actually equal to 2x. But if I take the derivative of y squared, okay, this is where it's going to be different. I still do the same thing. I bring the 2 down front, y. But then remember, this is the inside function. So the reason why it's only 2x is because dx dx is 1. But here I'm taking the derivative of y with respect to x. So I have to then multiply it by dy dx. So this is if you have trouble understanding that, just remember that if you're acting on y, the y has to be written as dy dx. Let's take a look and see how it works, okay? So we're just going to go right from left to right. So the derivative of x squared is just 2x. There's no y there, so it's just normal. Minus, I'm going to open a bracket here because that's going to turn out to be the product rule. So x times the derivative of y. X times the derivative of y. I'm not going to say the derivative of y is 1. It's actually dy dx. dy dx. Here's another way to think about it. If you have an x and you have a y, if I take the derivative of x with respect to x, well, you can think of them as differentials. Dx over dx, well, it almost looks like it's cancellation. But if I act d by dx on y, I get dy over dx. Okay, nothing to cancel. So when I'm acting on y, when I take the derivative of y with respect to x, it's got to be indicated as dy dx. Some teachers will actually just use y prime, a little bit easier to do. Okay, plus y times the derivative of x. Okay, so y times the derivative of x. Well, the derivative of x is just 1 with respect to x. Close. Okay, we got a y, so be careful. So I'm going to use the power rule. So I'm going to bring the 3 down front. So it's going to be 3y subtract 1. You still do all that stuff, but this here, I'm going to put a little box around the y. That's your inside function. There's your chain rule. So you're going to take the derivative of y, dy dx with respect to x. On the right-hand side, there's just the 1. The derivative of 1 is 0. Let me just sort of partition that. And now the goal is to isolate dy dx, okay? So essentially, you see I've got a term here and a term there that have a dy dx in it. So I'm just going to take that out. So dy dx with a bracket. This is positive and this is negative. I know the negative is going to come through. We're using our imagination here, okay? So this is going to be 3y squared minus x. Minus x. Sometimes I cut a few corners. I don't know if you do. Equals, and so here I've got to take this term over to the other side. And I also have to take this term over to the other side, not forgetting that the negative is acting on it. So a negative y on this side becomes positive y on the other side. And the 2x on this side becomes negative 2x on the other side. Are you with me? And now this is pretty easy because that's just a coefficient on dy dx. So I can divide both sides by 3y squared minus x. So dy dx becomes y minus 2x all over 3y squared minus x. I'll put a box around that. We're going to do a couple more so you get used to it, you get more practice. Okay, so this next one also is an implicit issue because look, inside cos you've got x and y. So let's just go from left to right. The derivative of x is 1 plus, well, what's the derivative of cosine? Well, it's negative sine. So negative sine, you rewrite this argument. You rewrite this angle, okay? It just gets rewritten. Then this becomes the inside part for the chain rule. You got the chain rule here too. So I'm going to take the derivative, that's going to be multiplied here. So I've got this multiplied by the derivative of the inside. The derivative of x is 1. And what's the derivative of y? dy dx. Good, good. So dy dx close equals, well, the derivative of 0 is 0. I have to isolate dy dx. So what I'm going to do here is, first of all, I'm just going to move the 1 over to the other side. And I'm also going to divide this. Okay, let me just clean it up. 1 minus the sine of x plus y times 1 plus dy dx equals 0. So I'm going to move this 1 over to the other side. And then I'm going to divide by negative sine x plus y. That's going to leave a 1 plus dy dx on the left-hand side. The 1 comes over, becomes negative 1. And then I'm going to divide by this. This will be the coefficient all over negative sine x plus y. And then to finish this off, I just have to move the 1 over. So finally, dy dx is equal to 1 over the sine of x plus y minus 1. And you can just leave it like that if you want to. You could also rewrite this as cosecant x plus y. Okay, the last one in the implicit section has some trigonometry in here. So what's the derivative of sine? Well, you know it's the cosine of x. There's nothing to do there. That is an inside function x, but the derivative of x with respect to x is just 1. Okay, next one. What's the derivative of cosine? Well, it's negative sine. So this is going to become positive sine. You rewrite the y, okay? Then you go inside. I'm going to put a little box around the x. That's the inside function multiplied by the derivative of y with respect to x. What's the derivative of y with respect to x? Well, how about dy dx? And the derivative of negative 2 is 0. I'm not going to write it. And the derivative of 0 is just 0. Okay, this is pretty good. So I'm going to say the sine of y times dy dx is equal to negative cosine x. And therefore, dy dx is equal to negative cosine x all over the sine of y. Be careful, do not turn that into a cotan because the angles are different. So that's where we stop. Okay, so these next few questions are going to refer to a table as opposed to using a lot of the algebra that we were doing. I like to put these on tests for kids that are learning their intuition on derivatives. The first one is telling us that there's a function a, which is really composed of adding f and 2g together. And what it wants to know is what's the derivative of a at 3. So because a is written in terms of f and g, I can use this table. You can see in the table it gives me information about f. So these are like the outputs for these given inputs. These are the outputs for g. It's like the y's for g, for these given inputs. And it also gives me the derivatives. So this can tell me, for instance, if I want to know the first derivative, what's the value of the first of f prime at 2, and it's equal to 3. Do you see how I can use that? Okay, so let's see. Let's start with this. So it says, hey, what's a prime of 3? Well, what's a prime? So a prime, or the first derivative of a, is going to be the derivative of f, since it's equal to that, the derivative of f, plus 2 times the derivative of g. And so I can use that. I can sort of think about it in terms of the input 3. So that means that a prime at 3, that's an a, is going to be equal to f prime at 3, my board is moving, plus 2 times g prime at 3. And I can get this information directly from the table. So f prime of 3, well, there's f prime, and this is where x is 3. So f prime of 3 is 4. So that's equal to 4 plus 2 times g prime at 3. Well, there's g prime at 3 is -1. So multiply that by -1, and the answer is going to be 4 plus 2 times -1, or it's going to be 2. Let's try this one here. This uses multiplication. So this is if you're studying composition of functions. So it wants to know b prime at 2. Well, let's find b prime first. So b prime is going to be equal to the derivative of f times g. Well, that's going to be first times the derivative of the second plus the second times the derivative of the first. So f times the derivative of g plus g times the derivative of f. So if I want to know b prime at 2, then I have to evaluate all of these parts at 2. It's kind of straightforward if you think about it. I think if you just sort of imagine what you would do, you'd probably get it right. Plus g at 2 times f prime at 2. So now it's just about evaluating. What's f at 2? Well, f at 2 is 5. I got to multiply that by g prime at 2. Well, here's g prime, and here's 2, so there's g prime at 2, -2. So I'm going to multiply that by -2. Plus g at 2. Well, g at 2 is 1, so multiply by 1. And f prime at 2 is 3, so I'll multiply that by 3. Do a little bit of bed mass here. 5 times -2 is -10. And also 1 times 3 is 3. So the final answer is -7. Okay, the third one that uses the table, they tell us that if d is equal to 1 over g, what's d prime at 1? So let's find d prime first. So d prime is going to be equal to, well, I can use the quotient law, bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom. So that's 1 times the derivative of g, which is g prime, all over g squared. I have to square the denominator. So if I want to know what d prime at 1 is, I have to evaluate each of those at 1. So g prime at 1 over g at 1 all squared. Don't get confused with your notation. So, well, okay, so g prime at 1. So g prime at 1 is -3. So that's going to be equal to -3, or a positive 3. And g at 1 is 3. 3 squared. Well, that's going to be equal to 1 over 3. All right, so this is the last question. So if you're still with me, I'm very proud of you. Okay, so this one has a sine and a cos. It's not really that difficult, but I wanted to get a second derivative in just to go through second derivatives. It's y equals a sine ct plus b cosine ct. So a, b, and c are constants. They're just numbers like 2 or 10 or what have you. And the goal is to find y double prime, so to find the second derivative. So let's first find the first derivative. So y prime is going to be equal to, well, the derivative of sine is cosine, right? And also, do you notice, are you getting good at it? Look here, this is the inside part. So I'm going to have to take the derivative of that. So the derivative of this term is going to be a, which has no real play in the calculation of the derivative. You just rewrite it. You're going to have to ultimately use the chain rule here. So I'm going to put that out front automatically. And the derivative of sine is cosine, and ct stays where it is, inside cos. Come to here, the derivative of cosine is negative sine. So that's going to turn negative, do you see? There's already a b out front. You're going to have to use the chain rule here for ct. So the derivative of ct, t is your independent variable, c is a constant, so you're going to get a c here, and that's going to turn into sine ct. Okay, well there's the first derivative. What about the second derivative? So we pick up where we left off. The second derivative is the derivative of the first derivative. So now we have an ac out front. This becomes the inside function, and I want the derivative of cosine. The derivative of cosine is negative sine. The a and the c are going to be there. They're just going to sit there. I know I have to take the derivative of ct. T is like your x. So the derivative of ct would be like cx would be c. So I'm going to get a c squared sine ct. Come here. What's the derivative of sine? It's cosine, positive cos. So that sine minus doesn't change. I know I'm going to have to incorporate the c into my coefficient. So I'm going to get b c squared. There's my chain rule, c for chain rule, cosine ct. All right, so there's my second derivative. I don't know. I always like to see if I can factorize. So we definitely have a c squared, which we can take out. We can take out a negative c squared, and that leaves us with an a sine ct plus b cosine ct. Do you notice something interesting here? That this is the original function y. So you could, if you wanted to, write that as double prime y equals minus c squared y. And that sort of sets us up for differential equations. Eventually, if you haven't used differential equations yet, you'll see those where you have equations with differentials in them or derivatives in them. Anyway, that's it. That's the 25 derivatives that I came up. I thought this would help you guys. If there's any special areas that you want me to go deeper, let me know in the comment section. And wow, if you stayed for all 25, please let me know in the comments if you made it to the very end. And I'll see you in the next video. I'm tired.